Alright, so now let's talk about what it means to be continuous at a point. So, a function y equals f of x is continuous at point c if the limit as x approaches c of f of x is f of c. So, what that last statement implies is that the limit as x approaches c of f of x exists if and only if the left and right limits are equal, and it also implies that the function value at c is, well, f of c. So when you plug in c, you get some constant value. These two c's are not necessarily the exact same number. So that's the only poor thing about these definitions. Alright, so especially useful for piecewise functions. So the following is another way to view the definition of continuity. So please, a lot of you guys are going to be good at checking the left-hand limit, the right-hand limit, but make sure you're also checking the value at that point. Make sure that all of these things are equal, so the limit as x approaches c from the left should be equal to the limit as x approaches c from the right, and the value of f of c all of those should be the exact same number. Alright, so going back to example 2, I guess, the last picture, it said for c is equal to 1, 2, and 4, find f of c, the limit as x approaches c from the right, the left of f of x, and find f of x if they exist. So can we see how all parts of the definition of continuity are important? So for c is equal to 1, we're going to zoom out just a little bit more so I can just have it all at once. So for c is equal to 1, the limit as x approaches c from the right, so coming in from the right, it should be at 1. The limit as x approaches c from the left should also be 1. But f of c is clear up here at 3. And again, these c's should all be 1s in this particular case, because all we're doing is looking at x is equal to 1 on that graph. Alright, so for c is equal to 2, so this time I'm just going to go straight in. Instead of saying x approaches c and whatnot, I'm just going to say x approaches 2, because all I'm doing is using this wonderful definition of continuity. So I've got the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and the actual value of f of 2. Alright, so the limit from the left, I'm going to grab a highlighter this time. So from the left, looking at this blue piece, it's going towards infinity. Coming from the right, that pinkish purple piece, also going towards infinity. And then finally at f of 2, we have no freaking clue. It's an asymptote. Alright, and then finally at c is equal to 4, so again, I'm just going to go straight in. Instead of saying limit as x approaches c, I'm just going to go ahead and plug in that 4. So limit as x approaches 4 from the left, limit as x approaches 4 from the right, and the actual value of f of 4. So 4 from the left is just going to be that green piece. And that green piece from the left is just approaching that value of y is equal to 3. The limit of 4 to the right, well, that's using that blue piece. Coming all the way up here. That particular function piece is approaching the y value of 2. And then finally, f of 4 is actually at 3. So, looking at how none of these match, there is not a continuous function all the way across, for one, and this would be how I find my points of discontinuity at this point. Alright. And so you guys can see that the value at C is not necessarily the same number. So like f of 1 was 3, f of 2 was actually not applicable, and the value of f of 4 was actually 3. So those quote-unquote C values aren't necessarily the exact same, is what I mean by that. I'm sorry if that part confused you guys. In this class, we use C a lot as a constant, and that's going to be kind of calculus's main thing, is that C is a constant or just some number. And that's all. Alright, so I think that's the only thing that I've said that's really, really, really confusing. I apologize.